He got his stuff turned in. He did the important things. All right, so we're going to talk about energy today and how we expend it. So we kind of talked about the chemistry of everything. And so now we're kind of taking the next step on that to why that chemistry stuff that we did in the last group actually applies to, let's say, the VO2 max test that you all are going to do, hopefully. So that's what we're going to do, how to measure, how to estimate, how to predict. There is a difference. And your energy expenditure at rest and during exercise. All right, review. What were the three things? Oops, they're already up there. So much for me making a really good... No transitions. I made that one and then got distracted, apparently. Shame on me. Oh, well. So, fats, carbs, and protein. Anybody remember the numbers? What do you got, Noah?
4 and 4 for carbs and protein, and 9 kilocalories per gram for fat.
That's really close. What was the exact number?
Oh, it's 9.
It's 4.1 and 9 points. Yeah, so a little more precise in this class compared to other ones. Glad you're feeling better.
Yeah. Sorry, I was late.
Yeah.
So, he let us out late for human Jefferson's class.
Ah, okay. You're good. We just got started. All right, so here's the things that you need to know. I think we had this very similar in the last, I think I even might have had the same slide. But I think there is a quiz question that has something to do with when you're resting. You have 50-50 on fats and carbs. That's what you're using. When you do a short exercise, you're going to be doing more carbs. When you do a long-term exercise, you're going to be doing more of the carbs and fats. So all those things in blue there. Eventually the blue things go away, but yeah, at least it's there. People are still typing, so I'll let you finish that, writing that out there. Mm-hmm. I was actually thinking that when you did it, and there were some other ones that someone talked about DOMS, which I think is tomorrow. Is when we talk about that. There's too many chapters, not enough days. I already added chapter 2 into this one. This year, like last year, I did an introduction, then I did a chapter 1, and then went to 5. But we kept referring back to things in chapter 2. So I was like, all right, we need to go over all that chemistry for a day. All right, and then here are the different supply systems from chapter 2. So there's another little review there. You have your fast one for your first first 15 seconds, less than a minute. Then your long-term here was you start oxidating fat and carbohydrates to keep your body going. So, all right, so how do they come up with all of this stuff? So after we get through our review. So they do what's called a bomb calorimeter. I don't know. So 1 calorie, we mentioned last time, is the heat required to raise 1 gram of water from 14.5 to 15.5 Celsius. And that 1 thing turns into a 1,000 calories, is 1 kcal, or 1 dietary calorie. They do this with what's called this bomb calorimeter. So they literally put the food inside of a drum, light it on fire, inside of a water container with a thermometer, and then, of course, you have to have oxygen to burn with and all that, something to keep the water consistently stirred. And when it goes from 14.5 to 15.5, that's how it's done. Takes quite a process to actually measure this, and there are dietitians and scientists that do this, and they think it's really fun to do that. I mean, burning things is fun and all, but I mean, burning random foods sometimes might not smell fun, so not really a major thing, but we're going to go into that same concept here. So you could actually do this for a human, where you have a room that you keep track of how long it takes you as a person to warm the water around the room in order to see how many calories you burn. Not very practical. There's a lot of things that can go wrong. But that's called a direct calorimeter. I don't even know how to pronounce it. That's how rarely this is used. So however much heat you have, has water going here. There's your air in and air out so you can breathe. And to keep it so you got carbon dioxide. And they would actually flow the same air through to make sure it's all the same temperature. And as the water comes out of here, that's what they would measure to see how much it goes up. So that's how it was done. That's where all these terms come from when they say how many calories you burn. They've actually somebody's done the work. We haven't done it. We're not going to do it because it's really not practical. So they have figured out using this method that the substrates that you're using is going to be 40% of that substrate energy is going to go to ATP, and 60% of it's going to go out as heat. So that's what they would be measuring in this room. So heat production increases with energy production. So this can be measured with that lovely calorimeter. So the water thrown through the walls, the body temperature increases the water temperature. So there are some good things about it. It is very accurate. It usually takes a while. This is not a short test. So I mean, somebody would have to be doing a jog for half an hour to an hour for it to really be able to measure and affect that. A short burst, you're not going to get that with. So these are a long thing, but they're really accurate at that point. Good for doing kind of resting metabolic measurements. So they could have you just sit in a room and measure how much the water around the room goes up, and that's how they can get that resting rate. Again, not practical, but it can be done. So expensive, 30 grand. That was 10 years ago, at least according to the video I watched a few minutes ago to get this thing. Probably more now. It's hard. There's some things that can make it not work right. Like if you're actually exercising, there's heat coming from the treadmill. There's friction from your feet, the motor running, that could also affect it. So there also, your body sweats is the countermeasure, and that would lower the heat measurement because of the evaporation of the sweat. So not really practical nor accurate really for exercise. More for like sitting in the room and getting how much it's using while you're sitting there. So that's why we tend to use in the exercise world the more indirect calorie measurements. So your estimated total body energy expenditure is based on your oxygen used to the carbon dioxide produced. So the measurements go as respiratory gas concentrations. It's accurate for steady state oxidative metabolism. So this would be a run or a cycle, kind of steady state, continuous, running on a treadmill, keeping a bike going type of exercise. So older methods of analysis are accurate but very slow. That's the other one we just kind of talked about there. New methods are faster, but they're also pretty darn expensive. All right, so here is some of the things that we'd hear. So you'd have your oxygen, so the volume of oxygen consumed, so that's how much is coming in. And then you take that volume inspired versus volume expired, so in and out. Then you'd measure the carbon dioxide, the volume expired versus the volume coming in. So as you breathe out, it measures, and it measures coming in and out, in and out. It's measuring both of these at the same time. This is what that machine upstairs does. So here is kind of the concepts here. So your body has all your food and uses oxygen, which turns into heat. And that's so we can measure the heat. We can measure through the other method. And then we can measure the oxygen, or the water, and the carbon dioxide that comes out. So 1 liter of oxygen consumed is 5 kcals, depending on the type of nutrient and all that. Anyways, but we'll just use that for now. So example, if you have 2 liters a minute of oxygen consumed, that's approximately 10 kcals, and you could even make that even further to kilojoules if you really want to get super, super technical. So your open circuit spirometry, otherwise known as a VO2 machine, its method for measuring that oxygen is going to measure the oxygen consumed, inspired, and expired. So here's what that could look like. That's a little nicer version than ours is. Ours makes a nice little printout. We don't get the cool screen to see everything at the same time. That would be cool, though. So you'd have a computer, you have some sort of mixing chamber, and then you'd have the gas analyzers of oxygen and carbon dioxide, and then you'd have some sort of gas volume. Our machine just does it all in one thing. This one actually has a little white thing right there. That's actually the gas volume, and then a two-way breathing valve around your face. So here's how that calculation would happen. So you have the weight of the subject, and we will put that in. You'll have your ventilation of let's just call this one 60 liters a minute. They have 20%, and 17% is how much comes in. That's how much goes out. Then you do the same thing for, continuing on. You multiply those together to get 2.4 liters of oxygen per minute. And that relative oxygen uptake would be, this is the amount in the room divided by how much the athlete is, and that would make your VO2, or at least the VO2 numbers. So there's just that's telling you what that machine is doing while you're taking that test. So there's another one called the Hadlane transformation. So the volume of inspired air may not actually equal the volume of expired carbon dioxide. So this one actually is going to do work with the volume of inspired nitrogen versus the volume of expired nitrogen. It's going to be a little more consistent. And there's a whole bunch of chemistry there that you don't need to know. Just know that there are calculations to do this. So it allows the volume of air to be directly calculated from the volume of expired air. So, and this will be to basically know that this Hadlane transformation is measuring nitrogen. That's what you guys need to know. This is another way of doing that. So there are different types of machines. Ours does oxygen and carbon dioxide. There are machines that will actually measure this as well. Maybe at the same time, maybe totally separate. Probably at the same time at this point. So the next one is the RER. Somebody talked about this in their journal the other day. So the respiratory exchange ratio. So O2 depends on the type of fuel being oxidized. So using glucose and acids, these all kind of go together. Lots more chemistry. So the respiratory rate exchange is the rate between carbon dioxide production and O2 usage. And this is usually done resting. So you get the RER, and we can do this with the machine upstairs as well. And that's where you come in before you've had your coffee, just woken up, sit there and breathe into this thing without getting your heart rate up to do it perfectly. We can't necessarily do that because you got to walk down here from your dorms or from your car. So there's just some more of that numbers there. So the RER of 0.7 is 100% fat. RER of 100 is going to be 100% carbohydrates. So that's where we can get this from, is we can predict what your body is using at what number. And so we can use this then with your VO2 max test to find what heart rate you need to be at to burn the most fat or to burn the most carbohydrates, depending on what you're training that you're going for. So it just depends. So we can use all this together. So 1 RER for is 1 molecule of glucose. Apparently that is a quiz question. And you could go through all the, 6 oxygens and carbohydrate, I forget what that molecule is, gets split into a bunch of ATP. And your RER of 6 in, 6 out to 1. So there's the calculation of why 1 RER is 1 molecule of glucose. So when you get the molecule of gluconic acid, which is how we know if it's carbohydrates or fats, depending on if it's 1 or 7, there's the chemistry that would be done for that, and it comes to 0.7. So I'll let you write that. 1 RER for gluconic acid, 1 RER for 1 molecule of glucose. There's your numbers there. And we can predict that substrate use with kilocalories and oxygen efficiency. So it's kind of cool that by taking a breathalyzer test while you're exercising, we can figure this out. It's pretty cool. I don't know why that's on there and it's blank. So there is the kind of chart there. We can go from 0.7 to 0.1. How much kcals are coming from carbs, coming from fats, and how that number would go all the way to 100 and all the way to 100 with how much oxygen is being used. Standing break. All right, simplifying this a little bit here. So let's see. You can estimate the energy expenditure. So generally speaking, everything has kind of gotten simpler. You don't have to hook up every single person unless you just want individualized data. Pretty much there have been enough data, enough people have run through that they pretty much have a pretty good idea of how much energy you're using if you're walking or running or cycling or pretty much any of those consistent ones. They haven't done as much on like weight training just because it's harder to measure, but any of these consistent, repetitious kind of motions, they can pretty much, and that's how Apple can say, you're using this many calories while you are running at this heart rate. Is they're taking the formulas that have been developed from studies and put them in your Apple Watch to tell you you are burning this many calories. So it's also pretty nice that there's kind of a linear relationship between how much oxygen you're using and how fast you're either walking or running. And here's an example of some of those calculations that are probably in your Apple Watch or Garmin watch or whatever things there. I think that's a kind of a repeat, is your production may not actually equal the exhalation, and we'll go into all that detail another day. RER is inaccurate for protein oxidation, because they, after you get past that in 0.7, and, it's pretty much not good to purposely starve somebody till they're using protein, so that's why they don't really know. So anywhere near 1 may also be inaccurate because the lactate buildup is going to increase your exhalation of carbon dioxide. So these are just some of those shortcomings that might be on a quiz question there. I don't have it listed as one of them, but might. So gluconeogenesis, I know we haven't talked about that, produces RER less than 7. So you can't just say because it's less than 7, it's protein. That's kind of where they're going with that one. All right, so there is another way to measure, and that's to use isotopic measurements. So this is an element that can do kind of an anatomical or atypical atomic weight. So this could be radioactive or non-radioactive. So basically they would give you a shot and then pull blood samples as you were exercising to get the how much of this is in your blood or not. So they would have it they would be traced throughout the body. So this deuterium, I can't pronounce things super well, is a common isotope for studying the energy of metabolism. It's fairly low risk and of CO2 production. It's ideal for long-term measurements. I've had a couple of, I don't even remember what it was called now, PAT scan? Is that what it's called? Where they actually give you a shot of low radiation things. And as they were doing this, I'm like, I'm walking back into this room. I had to go through a whole bunch of hallways, all weaving back in this hospital. And I'm seeing all these signs, radioactive this, radioactive this. I'm like, okay. And then I get in there, and the person that's giving the stuff, I expected him to be like in full radioactive gear. He wasn't. He's like, yeah, I have to wear this thing on my thing to say, here's how much radiation you've been around. He's like, it's so low, I don't even have to protect myself, and I'm around it for 8 hours a day. I'm like, okay, not as worried about it. So when they say low radiation, it's really, really low. They would just take measurements as you exercise. Literally taking blood work as you're exercising, that's tough. It's probably something they would do more on a bike than running. I've seen it done with a runner, and they actually keep the thing in your vein as you run. And then, it would be really awkward. But, the part that's in there is not a needle. It's a piece of plastic that's got a hole in it. And then it would come out to here, and they would just pop a thing, run for 3 minutes, and then you'd have to keep running and keep your arm straight. And they would slide the thing in and take another blood sample. And then they would measure that all out in the lab later. So not the best way of doing it, but it is possible. So the other one is going to be just heart rate monitors. This one's come a whole lot farther in the last 20 years. I probably started working with heart rate monitors probably 10 years ago when I first got into teaching. I remember I've still got some in my office there. They're probably 10 years old now. So based on the assumption that heart rate is linearly related to O2 or VO2. So they can determine a regression line to your heart rate. So this can estimate your VO2 from your heart rate in other exercise settings. So this is how your Apple Watch can say you have a VO2 max of this. It's really estimating it off of your heart rate and your steps and what you're doing. And again, it's using data and formulas from other things to try to give you that number. May or may not be accurate is the thing. So that's why I use doing an actual machine is going to be more accurate than this. But this is a whole lot more readily available. So it does have some limitations. Could be confounded by the ambient temperature in the room. That's why our lab up there actually has an air conditioner in it, so that we can control the temperature of the room. Upper body exercises versus lower body exercises, changes in your fitness level. It doesn't know that. So, as I say, this is all off of probably your Apple Watch. Poor correlation for low or sedentary and low intense activities. So having you just sit there and watch TV, it's not going to give you a good reading. Yeah. So I'll say those are just things that you need to know there. Pedometers are great. I used to have things for my students where they would like put it on their shoe or on their hip or something. I got a whole like 30 of them in there. You probably all need batteries, but yeah. So they just measure your steps, so they can be inaccurate. Different readings depending on where they're worn, depending on if it's on your foot, on your wrist, on your hip. They don't do things like anthropometric differences, how long your legs are, how long your arms are, how long your step is. So there's a lack of calibration, and this would be just on a straight one. Now, my first time I tried using pedometers for class, I had this like junior, senior class that only met once a week, or maybe didn't meet at all. I met like the first week and then basically gave them pedometers and let it go. And these things weren't the greatest things there, but they were only $30 a student, so the school was okay with paying that. And they had this like, it would give you a code after you exercise. You have to go for 3 minutes, and then it would start counting, and then it would tell you if you exercised for, I think it was 25 minutes, then it would give you a code that you would upload to something, and then that's how I gave them credit for it. Well, my students tried to come up with all kinds of ways to trick this. The best one was putting it on a dog. That one I thought was pretty brilliant. It was the dean's daughter, stuck it on the collar of their dog, and then went for a walk, and the dog got a whole lot more steps than they did. The worst one was a person decided to, by itself, throw it into the dryer. It didn't work because it just had a consistent, because it was by itself. If he'd thrown it in with clothes, it probably would have tumbled and done it down. But he threw it in by itself. It overheated and fried it. It didn't even give him a code. Because he tried it like with no heat, he tried it with heat he thought that would, I'm like, you tried this multiple times? Why didn't you just go exercise? By the time and he had to walk down 3 flights of stairs to go from freshman floor to the basement in order to do this. I'm like, you should have just walked the steps a few times, and you probably would have gotten the credits you needed. All right, so accelerometers are in every watch, every smartwatch now. And they can detect acceleration. It's also similar to the same method that a pedometer would. Now, the old pedometers actually had a thing inside there that you can literally hear it tap as you're walking. Accelerometers do all different directions, 360 degrees, and they can measure that into movement. And now your watch will use GPS along with that. Like, I can be riding down here from my house, and about the time I get by the grind, that's where it will always tell me, it looks like you're having a cycling workout. Would you like to hit start? I don't do it on the way down. I will do it on the way up, because riding down, I don't even have to pedal pretty much. So it records continuous data, quality time spent in different activities and different intensities. So you can actually get a little bit of different intensities with an accelerometer. Again, inaccurate when you're not moving is the main thing that's wrong with it. Oh man, self-reporting methods. So back in the day, before all this wonderful stuff, you would do an activity class, like jogging, for example. And the online jogging class, here's how you would turn things in. You would print off 10 charts, and you would just fill them out and turn them in once a week. Well, some colleagues of mine at Southern were telling me that they used to have a jogging class. Oh, they still do. And back when they had to do it as the self-reporting method, it was the class that had the most 100% in all of the entire university. Then they got polar watches for everyone in that class. The class went from the most 100% to the most failed class for the first 2 or 3 years they had it. Makes you really trust your students to lie on their activity charts, huh? So usually just like an activity questionnaire, and this is where it's used mostly in like studies, is like I tried this in mine for my master's project, is I had my students estimate how often they exercised every week. And I had some that said they were there 7 days. I exercise 7 days a week. I'm like, no, you don't. And then I actually compared that to how many students were at recreation time in the evening. How many of them were being active in the evening during that hour and 15-minute time? And I think, if I remember right, there were about 25% of the students were being active during that hour and a half or hour and 15 minutes that we had. The ones that said they were active X number of times a week was like 70%. I was like, the numbers were just totally off for how many actually were being active during, I mean, they could have exercised outside of that time, but really how many of them they were all in class or at work. So like, I don't think there was the 40% discrepancy of my students were actually exercising outside of that time. A few of them probably did. Let's see, predictive value, that's where they kind of already have it. Specific to your body mass, and divide that by the metabolic rate. So your resting is 3.5, energy to go horizontal, energy to go vertical, and all those things could be put together. I'm not sure what the question is here that's in this walking and running part here. So I'll say something's highlighted for you. So there are different kind of ergometers. So you can do a cycling one, which will do power, which is your resistance, how big the flywheel size, and then the cadence, how fast it's going. When you do this upstairs, you would actually put a cadence meter. I've got this on mine. I've got a exercise bike at home that I got during COVID. And that one I actually put on the pedal, and that gives me the cadence, and it'll connect to my phone. And the latest update on Apple Watches, they can actually connect now, and you can actually get watt. So more than power. So the energy up cost has 3 things: the unloaded cycling, external resistance, body weight. And we could probably actually see that whole thing there, but we're not probably going to have time. Let's see. So when you're at rest, so the metabolic rate of energy used by the body, so that would be the whole body oxygen consumption. So at rest, your RER is about 0.8, so that's further towards the carbohydrate side. And your VO2 is about 0.3 liters a minute, so at rest, your body needs about 2,000 calories a day. So that's why most of your dietary things are off of a 2,000 calories a day rating. So when they say your percentage of what you need in how many calories you need a day, or how many fats, all those things are all based off of this 2,000 calorie day that comes from the respiratory equivalent RER. So your basal metabolic rate is the rate of energy at rest. So this would be at a laying down position, a neutral environment, after 8 hours of sleep and 12 hours of fasting. So that's how you'd get that metabolic rate. So this would be related to the fat burning mass. So fat-free mass, kilograms, and this is also affected by surface area, age, stress, hormones, body temperature. So that one's not as easy to calculate as like RER would be. So your normal daily metabolic activity, is going to be like the BMR, but within 10 to 15%, so it's a little easier to get. So stringent standardized conditions are not required, like the 8 hours of sleep, 12 hours of fasting. So that's where it's going to be somewhere between 1,200 and 2,400 calories a day. And this is what you would get if you go to like MyFitnessPal and you put in there, how many calories do I need? I exercise this much per day. My weight is this. My height is this. This is where they would give you that number. So your total daily metabolic activity is going to range between 1,800 to 3,000. So depending on how active you are, competitive athletes can have up to 10,000 calories a day. I used to show a video in my health class. I can't find it anymore because it's not on YouTube, where they showed what Michael Phelps was eating while he was training. And it was like insane. It was like whole pizza, a gallon of milk, a pound of pasta, and that was his lunch. And then for supper, he'd have another pound of pasta. How many chicken breasts he ate, how many egg sandwiches he ate for breakfast. It was like 4 egg sandwiches. But then the guy would go train for 8 hours straight. Or for 4 hours, have lunch, take a little break, and then train for another 4 hours. So, I mean, when you're a competitive athlete, you could be eating a lot and gaining absolutely no weight because you're burning it all off. Standing break, last one. All right, keeping going. There's a chance we might get out of here early. Chance. Well, usually when I get to the last 15 minutes of class, I have like 30, 40 slides left. I only have 12. So we might get out early. We'll see. All right, so submaximal exercise, how much exercise you're using during that. So your metabolic rate increases the more you exercise, or the harder you go. So it's a slow component of uptake, or oxygen uptakes, high power outputs. You're going to have more oxygen. You're going to use more type 2 fibers to recruit. And so there's going to be a little bit of a VO2 drift. So an upward drift is observed at lower outputs, possibly due to ventilatory hormone changes as your body's trying to make more ATP and burn up things in your body. So the VO2 max test, so that is the point in which your oxygen consumption doesn't keep up with the intensity there. That's when you say, I'm done, and you quit. So the best single measurement in aerobic fitness. Not necessarily the best predictor of endurance performance. It'll be really interesting to see what Pablo's numbers are, because he is more of an endurance athlete. I did have one endurance athlete in here last year. It was and we have other cross-country people in here too. So it'll just be interesting to especially compare the two, or the multiple distance runners compared to, say, a volleyball athlete, which we have a couple of them back there. You know, where's their VO2 going to be in comparison? It'll just be kind of interesting. It's also fun to say, like last year I had the basketball team versus the soccer team. By the way, the soccer team won. Who had the most. Even though the basketball guy, one of them did really well. But like as a whole, the soccer team were more fit than the basketball team. So VO2 expresses in liters per minute, so it's just an easy standard unit. And it's suitable for all non-weight-bearing activities. VO2 max is normalized for body weight. An untrained woman or men's going to be 44 to 50 versus a young woman's going to be 38 to 42. I think our highest one last year was 62 is what one of the soccer guys got. So I mean, you can go this way. This is just average. So the difference between women's lower amount of fat-free mass and hemoglobin is probably what makes that difference. So here is the oxygen uptake versus the speed, and we will do the same thing. We'll do the speed every like 3 minutes or something like that. I don't remember what the number was. Where you're going to move it up a little bit, up, up, up. And here's where the untrained person, there's their max as they dropped off. Here's this person's max as they're more trained. So no activity is 100% aerobic or anaerobic, obviously because you got to breathe. So these are just estimates. So the exercise, post-exercise consumption is going to determine your lactate threshold. When we take that test up there, after you say, I'm done, then we slow it down to like 3.2 miles an hour, if I remember right. And then you walk for, I think it's 3 minutes, and it's going to keep measuring as you're going down, and it's going to figure out where your lactate threshold is as well, using your oxygen and carbon dioxide and heart rate all together. So as that all goes down, all the pathways are being used to re-up your ATP production. So exercise, post-exercise consumption, EPOC. We'll talk about that again later. So all the different levels, your ATP, PCR stores convert to lactate, which we all talked about that stuff in the last chapter. So as your oxygen consumption goes up, you start getting a deficit, steady state, and then when you finish your exercise, how quickly this goes back to the homeostasis for your body. Keep rolling here. All right, so your lactate threshold is the point at which the blood lactate accumulatively increases markedly, and they actually would probably test this by blood samples. Your light's on your phone there, man. So that production rate is going to be greater than the lactate clearance rate. So this is a good indicator for endurance athletes, is where you would want to actually measure, hopefully getting your lactate threshold higher and higher and higher in order to be able to run longer and faster at a more maintained speed. So it's usually expressed as a percentage of that VO2 max. So the higher the lactate threshold, the better the endurance performance is what you're hoping for. So for two athletes with the same VO2 max, the higher lactate threshold predicts the better performance, which would probably be the person that wins the race. So this is where, as they were talking about, where it just goes up exponentially. So the treadmill speed, the blood concentration, again, they probably did this by taking blood every 4 minutes or whatever, looks like every 2 minutes. And where it starts to go up, that's the lactate threshold that they're talking about. So athletes become more spilled, they use less energy for a given pace. So this is actually totally independent of VO2 max. The body learns to use better energy economy. That's why we train, so that we can go faster, and so because your body will adapt as you go, which is cool parts about the body. So multifaceted phenomena, some of that could be the distance of the race, better economy from practice, better movement form, and then a variety of types of exercises. So it looks like we have one runner that has a little bit better oxygen uptake, and then one that's a little less. So this would be their speed versus their oxygen uptake there. So a successful endurance athlete is going to have a high VO2 max, a high lactate threshold versus their VO2 max, and a high economy of effort. So between the two, better form, that kind of thing. So a higher percentage of type 1 muscle fibers are being used while they run, and recruitment of that. And again, you can train that as you go. So also the energy cost for different activities depends on the type and the intensity of the activity. So that is calculated from VO2 and expressed in calories per minute. So it ignores anaerobic aspects, so the EPOC. Daily expenditures are dependent on the activity level. That's probably the main part. And then the other age, gender, weight, free fatty acids.